Hey, let's get started. Hello, everybody. Welcome back to Markov chains or processes or whatever you want to call it. Your first homework has been posted and it is due a week from today, just before midnight at 11:59 p.m. We're going to submit homework through Gradescope, but even though I made a Gradescope account for this class, it is not yet linked to the Canvas page. I'm having some issues there. So that should be sorted out pretty quickly. Okay, so I have recapped on here the definition of a Markov chain or Markov process. So the word chain is generally reserved for a discrete time thing, but it's not all that important that you distinguish that. And Markov chains or processes, they can be in continuous time or discrete time, and they can live on continuous or discrete state spaces. And right now we're talking about discrete time, so time indices like 0, 1, 2, 3, and a discrete state space. And we're going to be talking about discrete for quite a while. So the definition of a Markov chain is a stochastic process that satisfies this thing, which is known as the Markov property. And you're absolutely right. Those of you who said, well, how do we define this in a continuous case? This definition would not make sense for a continuous, well, for both. So for continuous time and continuous spaces, but we'll get there. So what this says is here is your whole history of the chain. At time 0, your chain is at some point I0, which is just a point in the state space S. And at chain 1, you're at some I1, up through at time N, you're at some I. I could call that IN as well, but I really wanted these last two numbers to look a little cleaner. And that conditional probability is just the conditional probability of this. We don't need the past history of the chain. And that has to hold for all times n and for all points in the state space as long as the conditional probabilities are defined. Because you may have a Markov chain where, I don't know, there's something in this big long list that just can't even happen. And that's going to be in the denominator for a conditional probability. And that's going to make that thing undefined. But if that thing is missing over here, it may not cause a problem on that side. So that doesn't mean you don't have a Markov chain. It just means you don't worry about it in those cases where it's undefined. You only have to worry about the property when both sides are defined. Okay, so we were reviewing conditional probabilities, and last time we were mostly talking about events A and B, and we said that the probability that an event A happens given that B happens, so that horizontal line is read as given. This is a conditional probability. Someone has already given us the information that B happens. This is the probability that A intersect B happens over the probability that B happens. And we just started looking at this in terms of random variables. So now we're going to think of this as the probability that a random variable x equals x given y equals y. Excuse me. Now, this probability is going to be 0 if x is a continuous random variable. And I did a little bit tiny review last time of a probability mass function, but I haven't reviewed the continuous stuff yet. As I said, I just don't want to spend our whole first week in review mode. And since we're not doing continuous stuff for a while, I'm going to hold off on that. But for discrete random variables, this is going to be the probability that x equals x and y equals y. And we write and for random variables with a comma over the probability that y equals y. So same thing. And we're often going to want to, like I say, unravel the definition of conditional probability. And by that, I mean, no one else would know what you mean out in the world. But often we want to write an intersection probability, and it's more convenient to write it in terms of a conditional probability. So this would be like saying the probability that A given B happens, just taking the equation at the very top. This is the probability that A happens given B times the probability that B happens. And the same thing for the random variables, the joint probability that x equals x and y equals y is going to be the probability that x equals x given y equals y times the probability that y equals y. Or Actually, both of these could go the other way because the probabilities say that B given A happens. This is the this is the probability of the intersection over the probability of the second one. And the intersection, right? That's saying A happened and B happened. There's no real reason to write them in that order. You know, this next line here is just kind of a little silly. But you can see we can unravel this definition and we can write the intersection probability as a conditional probability times a so-called marginal probability, which is what you have when you have joint things you're talking about and you kind of restrict down to one of them. So check this out. Over here, I wrote the intersection probability one way, and here I wrote it another way. And we can do that with the random variables as well. And the game is usually just write it in terms of what you know or what you want, because you're going to have some kind of problem in front of you and you're going to have some information and not other information. So the game is always going to be to rewrite probabilities in a way that's useful to you. So please stop me if you have any questions. Again, feel free to speak up or put it in the chat, either for everyone or a direct message. That's okay too. So in our remaining brief review, I want to remind you of what a marginal probability is. So this is where you have more than one random variable and you know the joint probability for those random variables, and you remove some of them. So I'm just going to do it with two random variables going back down to one. The probability that a random variable x equals x can be written as the sum of the joint probability that x equals x and y equals y, and then you would sum out over all the y's. And the reason this is called a marginal probability is because joint probabilities for discrete random variables, you don't have to write this down, but they're often given in like a tabular form. Like maybe my random variable x can take on the values 5, 7, and 13, and my random variable y can take on 2 and 8. And then, oh man, I don't know that I can come up live with 6 numbers that add up to 1. So I'm gonna, okay, 0.1, 4, 5, 6, 7, 8. I don't know. Those are supposed to add up to 1. So if they don't, let it go. Okay, but these are probabilities representing, for example, the number 0.2 in here is the probability that x equals 5 and y equals 2. So that is 0.2. But if you want to know just the probability that x equals 5 and don't care about y, then that means you need to consider both of these cases. And if you add those probabilities, you'll find them in the margin. So the probability that x equals 5 is 0.3. And really, we got this by looking at the probability that x equals 5 and y equals 2, plus the probability that, x equals 5 and y equals 8. So we summed out one. And so that's why back up here, when you are going from a joint probability down to a single one, it's called a marginal probability. And actually, this could be a joint thing with like 10 random variables. And if you go down to maybe just a subset of 3 of them, that's also known as a marginal probability. So any sort of reduction in dimension. Okay, so one of our biggest tricks that we'll be using over and over again is, did I put a bullet? Yeah, I kind of have a bullet here, so I'm kind of going through like a bulleted list. Is the idea of computing a probability by conditioning on another random variable. So I'm going to call this bullet conditioning on y. So the scenario here is you want to compute a probability involving one random variable, and it's easier to, just because of the information you know, it's easier to bring in another random variable. So I'm going to write this as the sum over all y of the joint probability that x equals x and some other random variable y is equal to y. We just talked about that this is a marginal probability when you sum that out. but we also talked about the idea of unraveling conditional probability. I can rewrite the joint probability on the right-hand side as the probability that x equals x given y equals y times the probability that y equals y. So going all the way from this left side to this right side, what we're doing is finding the probability that x equals x by conditioning on y. And so you might get that as a hint in a homework, like hint, condition on the value of the Markov chain at time 2 or something like that. Okay, this thing I just circled in orange, especially if I did this with sets A and B, you might recognize this as the law of total probability. That's what it's called, but maybe you've only seen it for sets. So you kind of want one probability and you bring something else into the equation, but then you kind of run over all values, you total them all up. And if you've seen the law of total probability, you know what's coming next, and that is Bayes' rule. Bayes' rule. Bayes already has an S in his name. And this is, I like to say, for when conditional probabilities are backwards. What does that mean? I was going to do like an urn ball example, but I think I want to get to Markov chains, as I keep saying. But imagine really quick, I have 3 urns, it's always urns or boxes or drawers, right? I have 3 urns, and in each urn, I've got some number of red balls and some number of green balls. And maybe I randomly select an urn and then go in there and randomly select a ball. And I ask you, what is the probability it is a green ball? And given, don't write this down because it's going to be so sloppy and erased really quick. So I've got these urns and I've got maybe like 3 red, 2 green, 1 red, 1 green, 5 red, 6 green, or something like that. If I go into an urn, I select one at random and I ask, what is the probability of getting a green ball? It's easy to say, like, what is the probability you get a green ball given you went into urn 2? Because once you're in there, you've got a total of 2 balls to choose from, and 1 out of 2 of them are green. But if I were to ask you, okay, I'm going to randomly select an urn, go in, grab a ball at random. Now I'm going to look at it and say it's green. What was the probability I selected urn 2? That seems backwards. The probability we selected urn 2, given the ball we ultimately observe is green, doesn't it? It seems backwards, right? Because if you know you're in this urn, it's really easy to find the probability of a green. But if you have a green, now you have to sort of backtrack into which urn it came out of. And to me, I call this conditional probability like backwards. It's not what I want to see. And I want to flip it around. And that's when you use Bayes' rule. So I'm sorry in my rush that I didn't like write that example really nicely, but that's the idea behind Bayes' rule. And you have probably seen it with sets, but we're going to do, just like we did the law of total probability with random variables, we're going to look at Bayes' rule with random variables. So this is still, we're still under the same heading, but in case there's too many slides going by, I want to talk about Bayes' rule for continuous random variables. So suppose you want the probability that x equals x given y equals y. And for whatever reason, in the problem you're working with in your setup, you know the probability is the other way around. So we could memorize a rule, or we can just work this out, which is what I want to do, because I told you last time I don't really have a lot of brain space for rules. I'm just not good at memorization. So I would write this out as the definition. So it's a joint probability over a marginal probability. And then I would write that intersection on top using conditional probability. Oh, did I say continuous? Sorry. Yeah, I didn't mean to say continuous. Everything is discrete here, and that should be y equals y on the bottom. So I'm going to call that, you don't have to write this, but just if you're trying to figure out how this relates to earlier things I've said in this lecture, This is the unravel step where I rewrite that joint probability on top. There's two ways to do it, remember? And one way is just going to bring me back to the thing I don't know. So I'm going to write it the other way. The probability that y equals y given x equals x times the probability that x equals x. Yeah, and maybe you know all of these pieces, so you'd be done, like you can plug in the numbers now. But if you don't know the probability that y equals y, and it's easier to compute by dragging in the x, then you could, so this is actually Bayes' rule, but usually it's stated in the way I'm going to state it in the next line. I'm going to use the law of total probability to find that probability for y by conditioning on x. So in the numerator, I just have what I have. And then the denominator, we did this before in the other direction. I wrote the probability that x equals x by conditioning on y. So now I'm going to write this the other way around. This is the probability that y equals y given x equals x times the probability that x equals x summed over all the x values. And maybe that's a little confusing because in the numerator, I've got little x and little y. And that comes from whatever problem I'm trying to solve. In the denominator, I'm summing out over these values. So I wasn't sure if it was going to be more confusing to make these like, I and j. But just know that there's no little x and little y in the denominator, because when you compute, sorry, there is a little y. There's no little x in the denominator that will be summed out. So that's Bayes' rule from the perspective of discrete random variables. Okay, I have, I think one more thing to talk about before we can get back to the idea of a Markov chain. And that is, I'm going to call this double conditioning. And this can generalize to even more levels of conditioning. So suppose the goal is to compute a conditional probability this time. So to compute the probability that, say, x equals x given y equals y. So in what we did above, well, I don't want to make you dizzy with the scrolling, but in what we did above, we computed the probability that x equals x by conditioning on y. So there was no conditional probability in the problem to solve, but we brought one in. But now the goal is actually to find a conditional probability. And for some reason, and this is going to make more sense when we actually hit like word problems, for some reason, it might be easier to bring in a third random variable. So let's do this by, quote unquote, conditioning on a new random variable, z. If I was just, so this is a little parenthetical aside. If I was just finding the probability that x equals x by conditioning on z, then I would write this as the sum over z of the probability that x equals x given z equals z times the probability that z equals z. But now I've got the y in there. So I'm going to tell you what this is, but we need to prove that this is we need to prove that this is actually a true thing. So the probability that x equals x given y equals y, I'm going to drag in a z. Honestly, you can go straight to this, but because it's our first time seeing this, I think I will write out a few more steps. So this is the probability that again, up here, there were other steps. The first thing I did was write this as a joint probability of x equals x and y equals y and summed out the y's. Then I wrote the joint probability in that conditional times marginal form. So that's what I'm going to do here. This is x equals x and y equals y over the probability. You know what? I'm proving it. All right, I said I was just going to state it and not prove it, but let's prove it since we're on our way there. So I can write this like that. And in the numerator, I can make this, like I can bring in a third random variable as long as I sum it or marginalize it out. So I'm going to let z equals z and sum over all possible z. And now I'm going to unravel the definition of conditional probability to write the intersection as a conditional probability times a quote unquote marginal probability. And the game to play is, again, what do you need and what do you know? To get what I want, I'm going to think of this as like an event A and this as like an event B. And I'm going to use the fact that the probability of A intersect B can be written as the probability of A given B times the probability of B. Sorry, that might be a little cut off. And so in doing that and going back to what I was working on, this is the sum over Z of the probability X equals X given Y equals Y and Z equals Z times the probability that Y equals Y and Z equals Z over the probability that Y equals Y. The final thing I'm going to do here, again, I'm trying to go for this. I am going to combine. So this can come like inside the fraction. I'll write it this one time. I mean, this is like 1 over the probability that Y equals Y times a sum over Z. And I can bring this inside the sum. And so when I do, no, I don't expect you to write such detail, but just in case it's confusing for our first time through, I'm going to write this. So I've got the probability X equals X given Y equals Y and Z equals Z. And now I'm going to combine the two orange circles, and that will be the probability that Z equals Z given Y equals Y. So that's what the two orange circles become. Sorry, that's a little small, but I want to go back to what we started with. So in summary, here's what we just showed. The probability that X equals X given Y equals Y, we dragged a Z in, and this is the sum over all Z of the probability that X equals X given Y equals Y and Z equals Z times the probability that that Z equals Z given Y equals Y. Let me write the before again. If you want the probability that X equals X and you condition on Z, then that is really what I have in the line above, but in conditional space. So this is not really a notation that we're going to be using, but if I write, for example, the conditional probability that X equals X given Y equals Y, that's like, shrinking your Venn diagram and you're working in a new space and it's just probability all over again. So I might write this just for this one case as the probability that X equals X, and then put like a little Y here to say, you know what, we're in the conditional universe. We're in the conditional universe where Y equals Y. And so if you're in that conditional universe, check out this before line again. I'm going to put a little Y on all of these, right? That's just our original computing a probability by conditioning on another random variable, but it's all in the conditional universe. And so now I can put back the actual notation because this new subscript notation really means the probability that X equals X given Y equals Y. And on the right side, this is kind of the probability X equals X given Z equals Z. And you might say, but you'd be wrong, but let me write it, given Y equals Y. And this last one is the probability Z equals Z given Y equals Y. So all of the subscripts really represent given Y equals Y, but you never write this first term. If you are given information and given more information, then really you're just given a whole lot of information. So it would be really weird. I think people would know what you meant, but it's not good practice to write that. Really, this should be the probability that x equals x given both y equals y. Again, if you're given some information and given other information, you are given both of those pieces of information. So we already proved that this equals this, but the point of what I just wrote, I don't know if it was helpful or not, was to take an earlier conditioning on a random variable and just show that we're living in the universe that y equals y. So again, if you want the probability of x and you write it as the probability of x given z times the probability of z, but everything stays in the conditional universe, then you're really doing the same thing we did before. Before we get back to Markov processes, the game is always to write things in terms of what you know. I'm wasting a little bit of our time here, but just getting the foundation for conditional probabilities. So I just want to say that there are many ways to write kind of all probabilities. For example, going back to the set notation, let's look at the probability of the union of two events. If you want to find the probability that A union B happened, and you think of probability as area in Venn diagrams, then you have several ways to piece this together. So the probability that the event A union B happens, that area that I've just shaded can be made up of the area of A plus the area of B. But when I've done that, I have double counted the intersection, so we need to take that out. But it could also be made up of like this piece. I don't know if that color is very visible, and this piece, and finally the piece in the middle. So those are disjoint pieces. So I can write the probability of A union B as the probability of A, everything that's in A, but outside B, so intersected with B complement, plus everything that's both in A and B, plus everything that is in B intersected with A complement. So let me color code these. That's my yellow piece, that's my green piece, and that's my pink piece. So, you know, I just wrote this probability in two different ways, and I can write it in many more ways. I can just chunk up the problem and write it in terms of, you know, if I don't know the probability that A happens, but I instead know this probability, it's whatever you know. So the game is always to rewrite it in terms of whatever you know. I can give you other examples. We can, where I won't actually write them out and take that time, but we can write this union probability as everything that's in B. And then, oops, that was supposed to disappear. And then everything that is in A but not in B, and so on and so forth. So we can do the same sort of games with random variables. Okay. So let's get back to Markov processes or Markov chains, because I really want to get to the example. But before that, I need to talk about, so we're going back to Markov chains now, or Markov processes. And everything is discrete space and discrete time, and it will be that way for a while. So I'll write that a lot, but sometimes I just won't because I'm being lazy. So let's talk about missing time steps. Suppose, I want to put some actual numbers in here now. Suppose we have a Markov chain that takes integer values. Just because it's discrete does not mean integer values. If you want to find, say, the probability that x3 is 1, I'm just making some numbers up, given that x1 is 5 and x0 is 18. So you'll notice that x2 is missing. But the Markov property, and we need to prove this, the Markov property says, you know what, the most recent time step information is all you need. So this is the probability that x3 is 1 given x1 equals 5. Now our Markov property actually had all of the variables, so we don't know that this line is true, and we need to prove it. So last piece of information in time is really what matters. So I'm going to look at the left-hand side. This LHS is for left-hand side. And so that is the probability x3 is 1 given x1 is 5 and x0 equals 18. And given how we've defined Markov chains, I don't know how to deal with this because the x2 is missing. So I can bring it in and sum it out. This is the probability that x3 is 1 and x2 is some, I've been writing x, but now that I'm getting back to Markov chains, maybe we want things to look more integer valued. I don't know. This could absolutely be an x, but I'm going to say I given x1 is 5 and x0 is 18. And then I'm going to sum over all I, and make this big to make sure you can see. Well, I'll make it small first. Over all I in the state space. So S is the state space. That's where the random variables live. And then most of you know this, but just in case, this is an element of. And so this guy is saying sum over all of the values in the state space. And I could have gone straight to this line. I'm going to move this to the other side. I am going to unravel the intersection definition and write it as the probability of this given this times the probability of this, but I'm going to stay in conditional land. So this is the sum over all I in S of the probability x3 is 1 given x2 equals I times the probability x2 is I, but I'm going to stay in conditional land, which means I also have after the given sign these two things. x1 is 5, x0 is 18, and then x1 is 5, and x0 is 18. And now I'm not missing any time steps, so I can use the Markov property to say, you know what, I have this stuff is unimportant. And over on the right side, I've got this, so this piece is unimportant. So this is equal to the sum over all I in the set S of the probability that x3 is 1 given x2 is I times the probability x2 is I given x1 is 5. That past history doesn't matter. And that is the left-hand side. Okay, so rather than pushing forward and trying to make it look like the right-hand side, what I'm going to do is now start with the right-hand side and just see that it's the same thing. So the right-hand side was this guy. It's the probability x3 is 1 given x1 is 5. Oops, probability x3 is 1 given x1 is 5. So what the heck is that? Well, I can bring in x2. So I can do it in two steps. One is to write it as a joint probability and then turn it conditional by unraveling the definition of joint probability. Or since you know this law of total probability, you can go directly from here to here, right? That means compute this probability by conditioning on the value at time 2. That would take you directly to here. Just kind of for completeness here, I'll do the whole thing here. I can write this as the sum over all I in the state space of the joint probability that x3 is 1 and x2 equals I given x1 equals 5. And then I can unravel this intersection into the probability that x3 is 1 given x2 is I times the probability that x2 is I, but we're staying in the space where x1 is 5. So that just stays on the given side all the way through. And so I'm going to use the Markov property now. The Markov property says, you know what, at time 3, I just need to know where I was at time 2. Once that's given, I don't need to know past history. So this is the sum over all I in S of the probability x3 is 1 given x2 is I. And then there's nothing really to remove from this one. So this is the probability that x2 is I given x1 is 5. And in fact, we see that this thing is equal to what we got when we simplified the left-hand side. So the moral of that long story, please forgive the scroll, but I think it's more worth it than me taking the time to write it again, is if you have missing time steps and you have a Markov chain and you want to find some probability like this, it doesn't matter that x2 is not there. You just need to keep the last piece of information that was given, and then you can drop earlier stuff. And no, you don't have to show that each and every time. So if you want to just say this with like an MP for Markov property, it's all good. Unless the point of maybe a homework problem is to prove that this holds. Okay, I haven't quite gotten to the example yet, but this is almost an example of like why you would want to condition. It kind of could hold, like why you would choose to condition on a certain random variable. It is an example of computing a conditional probability, but dragging in another random variable. You know, it actually kind of works. And the reason is for a Markov chain, you know what, that's not a good example yet. Let me go a little bit further. So I guess one of the last things we can get into today is suppose we have a collection of random variables and it is a Markov chain on a discrete state space S. If it's a Markov chain, then we do know that the probability that xn plus 1 equals j given xn equals I and further back history that I'm writing as xn minus 1 equals in minus 1, x0 equals I0. We know that this, because it's a Markov chain, is equal to the probability that xn plus 1 equals j given xn equals I. If it's a Markov chain, that's the definition of a Markov chain. And I want to define something here. In the case where that probability on the right-hand side, the probability that xn plus 1 equals j given xn is equal to I, in the case where this does not depend on time, so does not depend on n or depend on time, on the time n, we have what is known as a time homogeneous Markov chain. So this is the definition of a time homogeneous Markov chain. And that is the default. That is by far the bulk of this class. So if I forget to say it, the only time you will have something that is not time homogeneous, we will see that eventually, but I will say this is not time homogeneous. And here is how this kind of transition probability actually depends on time. So this is the reason that I didn't continue this notation and call this in and in plus 1, because I thought that this line would be confusing. Because if I have an in and an in plus 1, then it depends on those values. And it might look like then it depends on n. But really, the distribution of this given this is not depending on n. So I don't know if that makes sense, but I think that what I'm trying to say, the reason I only used an I and a j and not an in and an in plus one, I think I can get that to make sense for you after a few more things. But given that we have a time homogeneous Markov chain, we want to talk about these so-called one-step transition probabilities. So I've got a time homogeneous Markov chain, and let's talk about one-step transition probabilities. And because they're not supposed to depend on time, I'm going to give them a new notation. We're going to call them, this is a lowercase p sub ij, and this is going to be notation for the probability that we move to j given we were at I. And as this notation suggests, it doesn't depend on n. We're in this time homogeneous case. And again, we are going to be in this, like you can always assume time homogeneity until you are specifically, directed otherwise. So this is called a one-step transition probability. It's the probability of going from state I to state j. So this is going to be the probability, this is going to be the probability that x1 is j given x0 is I, but it's also going to be the probability that x99 is j given x98 is I. And we're going to arrange these in a transition probability matrix or probability transition matrix. So arrange in a, I don't know, I say it both ways. So transition, oh, someone's waiting for a peanut. I forgot about him. Here you go. Transition probability matrix. Oh, such bad form to use abbreviations when you're defining something. But let's define a transition probability matrix right now in an example. So I've got discrete time, discrete space, and a Markov chain. So Xn, a Markov chain on the state space that is specifically consisting of the values 0, 1, and 2. Nice and discrete and even finite. So a transition probability matrix or probability transition matrix, we're going to denote this by some kind of like double-lined or boldface P to just differentiate it from our capital P for probability. In this case, it's going to be a 3x3 matrix, and I'm going to label the rows by the states and also the columns. And it's going to be filled with the probability of transitioning, say, from 0 to 0. That's called P sub 0, 0. And so let me fill all of these in. This is going to be lowercase p0, 0, p0, 1, p0, 2, and then the next row, p1, 0, p1, 1, p1, 2, p2, 0, p2, 1, p2, 2. So this is a transition probability matrix or a probability transition matrix. And sometimes our state spaces will be infinite, and we'll kind of write this looking infinite, but not right now. So note, last thing I think I can say, that we must have the rows summing to 1. Let's look at just like the one row. This means you're currently at state 1 and you move to state 0 with some probability, and you move to or stay at state 1 with some probability, or you move to state 2 in one time step. And you have to do something, especially when this is allowed, like staying where you are is allowed. So those 3 probabilities that I've circled have to add up to 1. And it's true of every row. And we're going to write this as, let me put an IE there, IE, the sum of Pij must equal 1. And that's if you sum over all j in the state space, and this has to hold for all I in the state space. The columns do not have to add up to 1. If they do, we've got a special situation going on, but they really don't. I'm out of time, but again, I promise you we will start. I'm not even going to do recap. We're going to start with a numerical example and go through a lot of example computations next time on Markov processes.